Hey, Gemini.
Hey there. I see you're working on a physics problem about buoyancy and fluid layers. That can be tricky. What specifically are you trying to figure out?
Can you help me solve this? First, can you read it just so I make sure that you understand it?
Okay, here's the problem. You've got an object that's submerged in a two-layer liquid. The top
No,
layer
I
has
mean,
a
like,
density.
can you actually read the text here just so I can make sure you understand exactly the prompt?
Okay, here it is. An object of density rho underscore object equals 2 rho is completely submerged in a two-layer liquid as shown below, where the top liquid has density rho underscore 1 equals rho, and the bottom liquid has density rho underscore 2 equals 4 rho. If the volume of fluid 1 displaced by the object is denoted by V underscore 1, and the volume of fluid 2 displaced by the object is denoted by V underscore 2, then determine V underscore 1, flush V underscore 1 plus V underscore 2, the fraction of the object which will be submerged in the lower liquid when the object is in equilibrium. Do you want to start breaking it down?
Yes. What else can you gather? Oh, yeah, the density of the object is 2 rho. Okay. So, how should I solve this problem? Can you walk me through it?
Let's solve this step by step. First, we need to use the principle of buoyancy, which states that the buoyant force on an object is equal to the weight of the fluid displaced by the object. Since the object is in equilibrium, the buoyant force must equal the weight of the object. Ready to move on to the next step?
Yes.
Next, we'll express the buoyant force and the weight of the object in terms of the given densities and volumes. Do you want to work through the math together?
Yeah, let's do it.
Sounds good. We know the buoyant force equals the weight of the object, so we can set up an equation using the densities and volumes. The buoyant force is rho v1g plus 4 rho v2 grams, and the weight of the object is 2 rho v1 plus v2g. Do you want to try setting those equal to each other?
You kind of said those pretty quickly. Can you repeat that one more time?
Sure thing. The buoyant force is density times v1 times g plus 4 times density times v2 times g. The weight of the object is 2 times density times the sum of v1 plus v2 times g. Does that make sense?
Wait, so this first part is what? The force? The buoyant force?
That's right. The first part is the buoyant force. Now let's write out the weight of the object. It's equal to 2 rho times the quantity v1 plus v2, all multiplied by g. Ready to write that out?
Yeah, can you repeat it one more time?
Okay, the weight of the object is 2 rho times the quantity v1 plus v2, all multiplied by g. Ready to write that out?
Okay, so what's the main formula that you're using here? Something with rho, vg, and force? What's like the standard formula?
The standard formula for buoyancy is buoyant force equals the weight of the displaced fluid. In our case, that's density times volume times the acceleration due to gravity. Does that make sense?
Density times volume, because that'll give you the mass. Or density, and then
Yes.
and then all divided by what?
We're not dividing here. The formula is density times volume times g. In your equation, density times volume gives you mass. Then, you multiply by g to get the weight.
Oh, the force. Okay, got it. But the density and volume is of the liquid, and then g is just gravity?
Exactly.
Oh,
The
that's an
density and
interesting
volume
formula.
are for the liquid displaced, and g is the acceleration due to gravity. So for the top liquid, it's rho v 1 gram, and for the bottom liquid, it's 4 rho v 2 grams. That gives us the total buoyant force.
Okay, and then we just have to find v1 and v2. So this one is the force of what?
That's the total buoyant force from both liquids combined.
Oh,
now
duh,
we just
okay,
need to
that's
solve for the
total.
fraction v1 over v1 plus v2.
Total.
Want to work through the algebra together?
So that's total buoyant force because it's the first one, the buoyancy of the first liquid is P, and then the volume displaced by it times G, And then 4p is the second liquid displaced this much times g. That's total buoyant force. Even though it's completely submerged, but it's still floating there, I guess, somehow. So it's like, okay. And then this one, 2p, v1 plus 2. What's this referring to?
That's the weight of the object itself. Now we're going to use those two equations to solve the problem. Do you want to work through the math together?
Wait, how did you get this as the weight of the object itself?
The weight of the object is equal to its mass times the acceleration due to gravity. The mass of the object is density times volume, and we know the object's density is 2 rho. Since the object is fully submerged, its volume is v1 plus v2. So the weight of the object is 2 rho, v1 plus v2g. Does that make sense?
Okay, so that makes sense. So that's the density times the volume of the water displaced. We'll give it the mass. Okay, so that's the weight of the object. Oh, and these two should equal each other because this is the total buoyant force and this is the weight of the object. And if it's not moving, then, and I guess that's in here, as shown below, top liquid, assuming that this thing is just like neutral. If the volume of liquid when displaced and volume of liquid 2 is v2, determine v2 over the sum of v1 plus 2, the fraction of the object which is submerged. Okay.
Great. So we've got the buoyant force equal to the weight of the object. Now let's write that out as an equation. It'll look like this.
Wait, but what are we actually determining here? Determine v2 over v1 over plus v2, the fraction of the object which will be submerged when the lower liquid, in the lower liquid, when the object is in equilibrium. What does that mean exactly?
You're right. We're solving for v2 slash v1 plus v2, which is the fraction of the object submerged in the lower liquid. We're getting close. Do you want to work through the algebra together?
Oh, basically just the ratio we're looking for.
Exactly. It's the ratio of the volume in the lower liquid to the total volume of the object. Ready to solve for it?
Yeah. Okay, so we can just here. How about I do it first and you tell me if I'm doing anything wrong?
Sounds great. Fire away.
Okay, so I'm going to open up this paper here. So I'll go the force of the buoyancy, V1G, plus 4 rho V2G equals 2 rho V1 plus V2G. So I wonder if we just cancel out all of these G's, and then we're left with, and then we take off 1 row, and we're left with V1 plus 3V2, I guess I'll just equals 2 V1 plus V2. Is that right so far?
You're on the right track. Just a small correction. When you divide 4 rho V2G by rho G, you should have 4 V2 left, not 3 volts 2. So the equation should be V1 plus 4 V2 equals 2, V1
so right.
plus V2.
I literally made that mistake. And I'm not dealing with exponents here. Wow, you did really well keeping track of that. That was an honest mistake on my part.
No problem. So distributing the 2 on the right side, we get V1 plus 4 V2 equals 2 V1 plus 2 volts 2. Now let's rearrange to solve for V1. What do you get?
All right, so we got 2 V1 plus 2 V2. And then we got here, but wait, we're looking for V2, whoops. Gotta move my mouse here so it wakes up. We're looking for V2 over V1 plus V2. So I can't really see, if we subtract I'm gonna just try this out. Is that all right?
Go for it. What do you get when you subtract 4 volts 2 from both sides?
All right, I get this minus 2v2. I feel like I'm not on the right track here.
Okay, so we have V1 equals 2 volts 1 minus 2 volts 2. Next, let's subtract V1 from both sides to isolate the V2 term. What does that give you?
Is it this?
Almost. When you subtract V1 from both sides, you should have 0 equals V1 to 2 volts 2. Now let's isolate V1 by adding 2 volts 2 to both sides.
Wait, so this is correct so far, right? I'm not crazy?
Yep, that's correct. Now let's add 2 volts 2 to both sides to isolate V1.
All right, so we get V1 equals 2v2.
Almost. Great. Now let's substitute V1 equals 2 volts 2 into our fraction V2, V1 plus V2. What do you get after substituting?
Oh, when we put it in there, so we're just solving for 1, then plugging it in there, and then we'll get the numerical ratio. Got it.
Exactly. So substituting V1 equals 2 volts 2 into V2 of V1 plus V2, we get V2 bulbar 2, V2 plus V2, which simplifies to V2 thirds of a volt 2. Then, the V2s cancel out, leaving us with 1/3. So the fraction of the object submerged in the lower liquid is 1/3. How does that sound?
So now this, so the amount that's the V2. So it doesn't matter if we solved for V1 or V2, we would still get 1/3.
Exactly. Whether you solve for V1 or V2, the fraction of the object submerged in the lower liquid is 1/3. Good job working through that.
And that's the amount that's displaced in this darker liquid, right? Not the lighter liquid up here.
You got it. So 1/3 of the object's volume is submerged in the darker liquid, and the other 2/3 is in the lighter liquid.
So that makes sense. Even though here it doesn't really look like it's only 1/3.
You're right, the diagram isn't to scale, but based on our calculations, it's definitely 1/3.
All right, sweet. Thanks so much.
You're welcome. I'm glad we could figure it out. Do you have any other questions about this?